Oh, I hear an
Everyone.
echo.
Hey everyone. So we are live now with the team from Zcoin. They'll be doing a talk around why trusted setup is no longer necessary for privacy. Would you guys mind giving a quick intro before you hop into your talk?
Sure. Like right now, are we live?
Yeah, you're live right now.
Okay, great. So Zcoin is a privacy coin. We've been around since 2016. We've been, I guess, like the pioneer of many privacy protocols. And I guess a bit about myself. My name is Ruben. I'm the project steward of the project. And let me move my slides. Give me a moment. And I've kind of been with them since the beginning, and I basically handle the overall strategy and operational aspects of the project. And Aram, who is also here with us, he's
Okay.
our cryptographer, and he's actually the creator of the Lelantus privacy protocol, which we will talk about later. And prior to developing Lelantus, I think he did a lot of pioneering work in proxy re-encryption algorithms and many other stuff, as you can see on the slide over there. Right? Anything I missed out, Aram?
No, it's fine. Just
Okay.
want to mention that I'm going back to my initial interest in cryptography. We started from a voting system.
Hmm. Okay, so before we actually even talk about trusted setup, I think it's worth kind of looking at kind of like the birth of privacy in cryptocurrency or on the blockchain, right? And I guess the very early variants was like coin join and ring signatures, and coin join, I think most people may have encountered it. It's like used in Samurai, Wasabi Wallet, and Dash, and there's variants in Bitcoin Cash. And the basic idea is that people bring their money together, put it in the table and kind of mix it up, and then take back money, the same amount that they placed in. And the basic idea is that you kind of adding plausible deniability, because then you are not really sure, well, whose note did you actually take? It could be anyone who was mixing with you. So I guess the idea is very similar to hiding in the crowd strategy. And it's not really completely hiding, it's more of like obfuscation. So it's kind of like adding noise into the mix. Now, ring signatures is, I guess, a more advanced way of mixing, because here, like in CoinJoin, you kind of have to actively mix with other people, while with ring signatures, it's done passively. So I don't have to say, I want to mix. You can just take other people's outputs and they can be selected as your plausible input. So there's no active mixing required. And you can even combine this with something called confidential transaction that even hides amounts. So, and this is actually used in Monero, which is, I think, the number one privacy coin in market cap right now. Now, I think it was just maybe like 1 or 2 years later, we start coming across like second generation privacy protocols, and they, the method is different. It's not so much about hiding in the crowd. It's more of like proving a valid transaction has happened without giving additional information about it. So in Zerocoin, which was, I think we used it from 2016 to July 2019. The basic idea was you could take coins with all this previous transaction history and then burn them. And then at any time in the future, you can redeem them for brand new ones with that are totally clean. That means it looks like it's been freshly mined. The performance was okay-ish. The verification time is constant. Basically, that means no matter how big the set was, the performance still held up. And it actually uses RSA accumulators, and it requires a trusted setup, which we will talk in the next slide. What is trusted setup? I think about 1 year later, after Zerocoin, there was another protocol called Zero Cash, which is actually now used in Zcash. And it uses more experimental mathematics and a much more complex construction, which we now know as ZK snarks. And it allows basically uses to perform, shielded transactions that do not really reveal the sender an amount. And the performance is really amazing. It's really quick, constant verification time. But again, it requires a trusted setup. So that's kind of like figure out like, okay, what is a trusted setup, right? And so any type of like zero knowledge arguments have trapdoors. Maybe Aram, you could give a brief explanation of trapdoors. Yeah.
Yeah, sure. So in cryptography, there are so-called one-way functions when the user can easily make computation in one direction, but he cannot make a backward computations without owning this special type of information referred as trapdoor. So Trapdoor basically enables the user to make fast computation for specific function, which could not be possible otherwise. In the context of our cryptocurrency, for example, or Zcoin or zero cash, the user owning the trapdoor could be able to fake the proofs, to make computations without knowing the actual witness for the transactions you want to perform. That's why this is very important that the trapdoors are hidden or destroyed.
Right. So basic. Yeah. So should I?
No,
Yeah.
go
So
ahead, please.
basically, with trapdoors, some are random. Like for example, with Atlantis, Sigma, Bulletproof, and Starks, there is a trapdoor, but the trapdoor is random, so there's not actually someone retaining it. While other types of trapdoors, such as used in ZK snarks and many of the newer snark constructions, require what we call a trusted setup. So a trusted setup isn't really good. And the basic idea of a trusted setup is that to create the system, I need to have some initial parameters. And those parameters, I need to destroy them. If I don't destroy them, it's basically, well, a trapdoor or a backdoor into the system. And in the context of cryptocurrencies, if I do have this initial parameters, as some people call it toxic waste, I can, as Aram said, generate fake zero knowledge proofs. That means I can generate coins out of thin air. So that's really something what we don't want. Now, even if the trapdoor is revealed, just to let people know, the anonymity is still preserved in most cases. But again, it doesn't matter if you have like privacy, but your coin is being inflated and has no value. So how do I actually ensure that I destroy this parameter? So this is only required in cases where there is trusted setup. And so I think the most famous one, which was carried out by Zcash, which was the initial setup ceremony for the Zcash protocol. And the idea is that instead of one person generating the trapdoor, the parameters, which is obviously not good because then he has ultimate power and you have to trust him to destroy it. Instead, they devise a ceremony that instead of one person generating the parameters, everyone generates their own little part. And as long as one participant destroys it, then the trapdoor is hidden. That means your system is secure as long as one honest party destroys it. And that's in theory, of course. Now, in actuality, it can be a lot more complicated. For the initial setup ceremony for Zcash, there was only 6 people. And many of them were also affiliated with the Zcash protocol. So there is, of course, the issue of like, how do I select my participants, right? Of course, they tried to get, some outsider, Peter Todd, who actually spoke very vehemently against the setup ceremony later on. But there are other types of attack vectors. So even if the math is correct, even if the ceremony is correct, let's say if your computers are compromised, or let's say a dependency when you were building the code for the ceremony was compromised, there are other kinds of attack vectors. So even if you have all this nice math to split everything up, if there's any step of the way that I could insert a backdoor and extract certain things, there's that potential that something goes wrong. Now, when you're building something that you want, several $1 billion worth of money, that's obviously not great. And even if you do all of this, key generation can be done wrongly. And this has actually kind of happened with the Zcash sprout ceremony, where I think certain, maybe like, I guess we don't go too detailed into them. But what happened was there was an issue that actually would have allowed coins to be created out of thin air. And they had to fix it in the latest sapling ceremony. Now, the other bad thing about having in this particular construction, the ceremony has to be redone every time you want to change something. So, you go through this entire process of like, destroying and setting this all up. But let's say if I want to change a parameter, if I want to improve the construction, somehow I need to redo the ceremony again. So it's quite cumbersome in this case. And not all setup ceremonies are like this. I guess Aram can talk a little bit about the RSA. What was the setup ceremony in Zcoin itself that we use, which is different.
Yeah. So Zcoin was using RSA challenges, and of course, knowing RSA factors would enable the user to create to fake the proof, or break the proofs and break the anonymity. That's why it was very important to find the RSA numbers with no known factors. How to generate the number and will not leave as a toxic waste. So the authors went to find similar numbers in the Wild West. There have been RSA numbers generated 20 years ago, and so the factors have been destroyed, and there was a challenge asking the cryptographers or everyone to break the challenge. So it was not broken, so it was considered to be secure. But
so
if
I guess,
was someone knowing the RSA factors, he could easily break the whole Zcoin security, create money out of thin air, and even break anonymity in some context.
The basic idea is that I guess the ceremony in that case was outsourced to a ceremony that was done long time ago, that was not even for the cryptocurrency, not done by the creators of the thing, and assumed to be secure. And it's quite hard to actually find such ceremonies because they're really, really rare. I think in that case we were really lucky to have that. But it is not easily replicable as as if you come up with something completely new, you might have to do your own ceremony. But it just kind of illustrates that there are different ways to take trusted setups. Some are worse, some are better. Now, I guess I kind of like to liken trusted setup kind of like to Lord of the Rings, right? So you have all these rings of power which gives lots and lots of lots of abilities and powers, right? And the idea is that there was this one ring that basically kind of had dominion over all these rings, and it's kind of similar, right? Like you have like participants in your setup ceremony, but you must destroy the one ring, because if someone manages to retain that one ring or reforge that ring together, then he has control over all the other rings. Of course, it's I guess similar in the sense that you need to destroy the one ring to ensure that the system is good. And I guess another way of looking at it is like, Frodo, he used the ring for ultimate privacy, make himself disappear, but at the cost of corrupting his soul. So it is very powerful. Some setups with not all certain constructions with trusted setup can be very efficient. But they come at the cost of having to make sure that this trusted setup, this initial parameters were not compromised in any way. And that's quite a hard task. So obviously it's not a desirable thing. Now, with newer kind of smart constructions, they try to mitigate this. So they don't remove the requirement for trusted setup. And these are used in like Sonic, Supersonic, Marlin, Plonk, just to name a few. And the idea is that although I have a trusted setup, let's say, a group of 6 people, I don't like these people, I don't trust them, I want to be a participant in it. Even when the system is already live, I can add my own like random data to it and be a participant to this like ceremony. So the idea is that it is an updatable kind of trusted setup. So as long as one user has participated, like one honest user, and actually has destroyed it, the system is secure. So I would say that this is almost untrusted setup. It is still a trusted setup, but the chances of like, because if you're not satisfied with the trusted setup, you can just make sure that you destroy your own parameters and the whole system is secure. So I think this is actually very promising. It's still very highly efficient. But again, it's still trusted setup. There still needs to be that ceremony and whatnot. But and these constructions are still rather complex, and many of them still use very exotic math. So when we say exotic math, they rely on what we call non-standard cryptographic assumptions. Cryptography that's really, really new and hasn't really been better tested, those assumptions. So we were thinking like, look, this type of like smart constructions are very complex, and with the complexity you can prove all sorts of arguments. I can prove many types of things, but in privacy, in cryptocurrency, it's a much smaller set of things that I need to hide, and you don't need so, like, I would say, like complex circuits to do that. And the basic idea in cryptocurrency, if you want to provide privacy, you need to hide amounts. You want to hide, how much you're sending, right? Or you're receiving. You want to hide the source of these funds and hide the receiver as well. And you also want to hide metadata like your IP address and timing. Of course, this can't really be addressed with, let's say, like a blockchain privacy protocol. That has to be like another layer, like you use Tor or use Dandelion or use one kind of mixed net. But the idea is that as long as you protect these three things, you would have a private cryptocurrency. So when we were designing Lelantis, basically, we had certain goals in mind, and maybe Aram can go through some of those goals.
Yeah, sure. So obviously the first goal of a privacy payment protocol is to ensure high anonymity for the transaction and also confidentiality of transfer amounts. So this was in our mind, but we wanted the construction to not be complex, but to a very intuitive construction, to be based on standard cryptographic assumption. We wanted it to be easy to implement, easy to cryptanalyze, easy to test, so it could find a wider adoption and be used by other developers as well. And of course, the performance and proof sizes are very, very important. It should be competitive with all these efficient zk-SNARK constructions and others generic zero-knowledge proof techniques in order to be scalable. And I think Lelantus satisfies all these goals. I think we can go into some details during the next slide. Ruben, maybe you will explain the basic approach before discussing the performance.
So, I guess one of the benefits of having a simple construction is that if you only need certain types of things, less things can go wrong, because it's much easier to audit, it's much easier to implement, and you still get really good performance, and you're not taking really unnecessary risks with really experimental math that maybe only a few people in the world understand. So I think that's a really big benefit, especially when you're looking at it for what we call like currency that we're not supposed to trust anybody, right? But if the math is so complex, we kind of have to trust the mathematicians that kind of created it. So simple constructions allow, I guess, a wider audience of people to understand the protocol and say, yep, I get how all these things work, rather than having some sort of moon math working in the background and just believing it works. So I think that's a really important distinction, especially if you want to be a decentralized cryptocurrency that's not reliant on the single team. Now, in terms of how Lelantis works, it kind of works similar to Zcoin, where again, you can burn coins and then you can redeem them for brand new ones at any time in the future with no previous transaction history. But the difference is that we can do this with any arbitrary amounts. That means I can burn let's say I burn 100 76.2 coins, and then I can redeem partially maybe 2 coins. Now with the earlier constructions, you kind of have to redeem and burn and redeem in the same amount, like a burn 10 and redeem 10. But here now you can redeem in partial amounts, which is a huge improvement in privacy, because then you can't really tell, well, where did this come from? Did it come from the 10? Did it come from the 100, or whatever arbitrary amount that was burned? Now, it can even actually be made much more powerful. I don't even have to redeem the coins and show like its value. I can actually pass this right to redeem to someone else. So let's say I burned 173 coins. I don't want to redeem it. I can pass that right to redeem. Like, let's say, okay, I give you the right to redeem 5 coins from my balance to you. Then you can redeem it, or you can transfer it to someone else. So in those cases, the privacy is really high. You're hiding the amounts, you're hiding the sender, and it's just really, I would say, very, very high levels of privacy. And it's much better than, I would say, obfuscation techniques and mixing, where it's kind of dependent on how many people you're mixing with. It's more about, look, everyone that has burned coins, everyone that has done the transaction, that like anonymity set is a much larger. And I guess a very easy way to kind of explain this is kind of like, imagine like footprints on a beach, right? Let's say you have some footprints on the beach and you want to hide your footprints. The way other kind of models work, such as Monero, CoinJoin, even Mimblewimble, is kind of like putting many footprints around the sand. So you kind of obfuscating you're adding noise around your footprints. So you're like, I'm not sure this trail of footprints goes where, right? But again, it's only, you're not hiding it, you're just obfuscating it. While the way that this kind of like zero knowledge proof, like burn and redeem mechanisms work, it's almost like the wave comes and washes it away, and your footprints are gone. So we do think this is a more like preferable privacy model, and we're actually more breaking the link rather than just hiding the link in the crowd.
Which was found to be not secure enough, right, by other researchers, for example, by Jan Mears.
There's been some research that if you do multiple transactions, there's that common taint that decoy models kind of break down, but probably beyond the scope of this talk. But yeah, so Aram, do you want to kind of run us through like how Lelantus compares in performance compared to other privacy protocols? Yeah.
Right. So I think as we have been discussing anonymity, better to start from this feature. The goal was to ensure high anonymity. We can see that Monero, for example, as it hides in the crowd, it obfuscates the transaction within another 11 transactions. And it has been found to be absolutely not secure against different types of attacks. In the opposite, Zcash hides the transaction within 4 billion transactions. So basically, it erases the link of your transaction and its origin. Lelantus provides some trade-off with this tool, and it can ensure up to 100,000 anonymity set. Actually, we can move into bigger anonymity set with a recent update of our protocol, but we will talk about this later. Now our aim is to ensure an anonymity set of size from 65,000 to 100,000, which will ensure pretty good anonymity and make the system immune against existing statistical attacks. We don't use trusted setup. The proof sizes are, again, quite competitive. They are around 1 kilobyte to 1.5 kilobyte, which is good. It's better than in Monero. Of course, it's hard to beat Zcash proof sizes, which are few hundred bytes, but still 1.5 kilobyte is scalable. And it's okay. It will not become a bottleneck for making a scalable cryptocurrency. Proof time is very competitive. It's faster than Snarks. It's similar to Monero, but again, what to just remember that we are providing anonymity, higher anonymity than Monero. And the verification time, which is considered to be one of the most important features, because when you run some decentralized application and you require all nodes to make verification of all transactions happening in the network, verification time is super important. And snarks are providing super fast verification. It goes down to a few milliseconds. With the recent update, it is about 2 or 5 milliseconds. But we could reach to the 30 millisecond for the anonymity set of 100,000, which is still pretty good. I think these few features summarize the performance of the privacy payment systems. And last thing to mention is Lelantus is based on standard cryptographic assumptions. It relies on discrete logarithm assumption, which has been there for a few decades. It's widely used in digital signature in many other crypto systems all over the world.
So, just quick one for those who don't know, like proving time is basically the time to generate the proof. So if I want to do a private transaction, how long is it going to take, right? Because like really early variants of zero cash could take 40 seconds to generate a private transaction on a powerful computer. And that's kind of like a really bad user experience because that's been brought down. And, if you have a 40 seconds on your desktop computer, on a mobile, it's like practically impossible. Well, like you're going to be waiting minutes there. So proving time should be relatively quick so that, your mobile can do it, your computer can do it with not too much waiting time. And verification time is for other people to check, okay, is this proof valid or not? And it's really important, especially if you have thousands of transactions coming in. You want to make sure that the nodes are keeping up in processing these transactions. So that's kind of how it fits in the cryptocurrency sense. So one of the other things that Aram has been working on is that we have been looking at improvements of Lelantus. So this performance figures are decent already, but it can actually be improved quite greatly if we change some of the curves like Ristretto curves, or we implement like one of our actually more innovations, which is called hierarchical one of many proofs, which can actually bring proof times by about an order of magnitude, which is like 10 times. So like if it's like 1 second now, it's going to take like 0.1 seconds. Those things aren't live, not coming in the first iteration. We still need some work to integrate it. But it shows that this protocol is not at a standstill. It still can actually be brought a lot more efficient. And, we really, really look forward to pushing the boundaries of this. Just very quickly, before, just for people who want to know, there are a few building blocks in Lelantus. The first one, which is the one of many proof constructions, basically the proof that you're one of the many that has burnt your coins without showing which of the coins you burnt. This construction was actually like in 2014 by really famous cryptographers like Jens Grot. And then we use bullet proofs for range proofs, basically the proof that the transaction is not a negative value or an infinity value, and a balance proof to make sure that, when I'm sending you a private transaction, although I'm not revealing the amounts, I'm making sure the inputs and the outputs balance. That means the in and the outs are balanced. And that's why you don't want the negative values, right? So you don't want to create coins out of thin air. Now, Lelantus isn't the only construction without without like a trustless setup. With a trustless setup, there's stuff like Stocks, which is very famous. It's fast, no exotic math, standard cryptographic assumptions, but the proof sizes are really, really large. I think the first iteration was maybe 200 kilobytes, which is like a lot. I think they've been able to bring it down to 50 to 100, which is still a lot. So it has its own applications, but probably not great for a privacy cryptocurrency. Halo is something that Zcash is working on. It has no trusted setup, but it has linear verification time. That means as the set grows, the verification time does increase. So it's not as efficient as, let's say, something like ZK Snarks. There's a very, very new promising construction. I think it was maybe just a month old. Well, it's not a month old, but they kind of updated the paper maybe just like a few weeks ago. And it's a very new, promising construction from Microsoft with no trusted setup and very fast proving time. But we still have to check on the verification time figures as well. Bulletproofs, everyone has heard of them, but most of the time, bulletproofs are only used as range proofs. That means range proofs to prove that a very specific thing. Is it make sure that the figures are non-negative and not infinity or within a certain range, and those bulletproofs can be quite efficient. But if I want to use bulletproofs to prove more complex statements, it is very, very, very slow. This is actually something we tried and just abandoned, and that's why we kind of went with Lelantus. So yeah, the space is moving so quickly. I think like cryptocurrency is actually push you know this might have taken like, I don't know, 10, 15, 20 years to develop all this body of work, but because of cryptocurrencies, because of blockchain, I think this has all been done in the past 2 or 3 years. So this is pretty cutting edge and really amazing tech. So yeah, I mean, if anyone wants to find out more about us, you can go to our website, join our Telegram, or take a look at lelantus.io, which has all the academic papers, if that's your thing. And
yeah, this was fantastic. We're going to
Yeah.
transition now to our next presentation.
Sure. Right.
Awesome. Thanks so much.
Thank you.
Take care. Bye.
Bye.